previous lecture we started our discussion with isolated magnetic moments, and we found out that whenever we have some angular momentum associated with it, there is a magnetic moment. And we looked at how these magnetic moments energetically change when they are placed inside a magnetic field. And from this we looked at the idea of paramagnetism. And we found out that for a spin half system, if J equals 1/2, that is, it's a spin half system, we found out that the magnetization with respect to the saturation magnetization is given by tanh of mu b b over kVt. And from this we derived the Curie's law as well. We found out that in the high temperature approximation, the magnetization is inversely proportional to the temperature. And if we plot this magnetization as a function of this object, let's call this object y. If you plot this function, the shape is like this. It's a tanh function. It saturates at a certain value of magnetic field or temperature. The temperature must be low and the field must be higher for this paramagnetic material to saturate. And a gas of electrons, for example, or a gas of protons, and if you only consider their spins, is going to be paramagnetic. Now, in the last lecture, we finished off our discussion by looking at an arbitrary J. So, Muzammil, were you able to derive the magnetization for an arbitrary J substance? No, were you able to do it? Okay, अभी तक नहीं किया नहीं है. Kiya. All right. So let me review this quickly. Suppose you have an arbitrary J, which means J could be half, 1, 3/2, etc. The partition function for such an arbitrary J material is of course given by the sum of the exponent of the energies. Right? And the energies are given by minus of Gj mu b mj b, where b is the field, divided by kVt. And the two minus signs, they interact to give you a plus sign here. So you find this sum over mj from minus j to plus j. This gives you the partition function. Okay, and we know what the values of mj are. We know that gj could in general be different from 2. For an isolated spin half particle, an electron, this is 2. But for an arbitrary j, this could be anything. On anything, it could be different. So if we make the assumption that I call this object x, then this is simply the sum of exponent mjx. So it's a geometric progression, a finite geometric progression. And this turns out to be equal to, the lowest value is minus j, the topmost value is j. So this turns out to be e raised to the power minus jx, 1 minus e. Now there are two j plus 1 terms. Okay, x divided by 1 minus e r. Okay, this is simply the partition function. Now we can simplify this a little bit. We are fond of hyperbolic trigonometric functions because we have a hyperbolic trigonometric function here. So we can simplify this slightly in the following fashion. This e minus jx remains what it already is. I take e raised to the power 2j plus 1 over 2x as common, and I'm left with e j minus j plus 1 half x plus e raised to the power 2j plus 1 over 2x e raised to power 2j plus 1 over 2x, right? Divided by e x over 2 I take as common, e raised to power minus x over 2 plus e raised to power x over 2. Okay, so I just cunningly take these factors out as common, and my partition function then reduces to a somewhat simpler form, e raised to power minus jx e raised to power j plus half x e raised to power minus x by 2, and the numerator could be replaced by both. Oh, sorry, this is minus and this is a minus, sorry. So this becomes sinh of j plus half x divided by sinh of x by 2, right? And I can simplify this a little bit. So this just goes away, and I'm left with the partition function, which is sinh of j plus half x divided by sinh of x by 2. So I've calculated the partition function. Now I need to calculate the magnetization. The magnetization is given by 1 over the partition function. 1 of the partition function is sinh of j plus half x. In the numerator we have sinh of x over 2. And we have to take the sum, and we find out the energy of each mj state. The energy of each mj state is given, the magnetization of each mj state, sorry, that's given by gj mu b mj, right? This is the magnetization of each mj state, and we multiply this with the fractional population. The fractional population is exponent minus g b u b n j b over k b t, right? So this is the magnetization of such a material. Now if you notice here, what we have here is, once again I could replace this term with an x. Okay, so I have sinh of x over 2 divided by sinh of j plus half x, gj mu b is a constant, I can take this outside, and I'm left with the sum over mj of mj exponent minus mjx. Now if you look at the partition function, if you look at this term, this is related to the partition function. The partition function is, as you could well imagine, is given by exponent minus or plus mjx, sum over mj. By the way, this is plus here. Okay. Now if you look at the partition function, is this term somehow related to the partition function? If I take the derivative of the partition function. The derivative of the partition function with respect to x is going to be given by nj exponent njx, right? So this thing is in fact the derivative of the partition function. So what we now have, this is 1 over z, all right, gj mu b, the derivative of the partition function with respect to x. And this is simply gj mu b, the derivative with respect to x of the natural log of z. So this is the magnetization. Now I know what the partition function is. This is the partition function here. I can find the log of the partition function, right? So if I find the log of this partition function, I take the log of the sinh minus of the log of the numerator minus the log of the denominator, and then I can find its derivative, and I can find out what the magnetization is. And this magnetization, would you mind just performing this calculation in the next 1 or 2 minutes? Just perform this calculation and find out what is the final result that you get for the magnetization. With respect to x of natural log of z is sinh j plus half x. The derivative of this, which is cosine of j plus half x, and multiply this with j plus half, okay, minus cosine of x over 2 divided by sinh of x over 2 into 1 over 2. I can write this thing over here as 2j plus 1 j plus half, this is 2j plus 1. So this thing is simply cotangent h of j plus half x, 2j plus half over 2 term here, minus 1/2 cotangent h x over 2. Okay, and I would like to multiply this with gj mu b, gj mu b. Okay, I would like to divide by j, I would like to multiply with j. Okay, this is my magnetization for an arbitrary spin system, and it's a paramagnetic system. You have spins pointing in different directions, and when we place it inside a magnetic field, a magnetization builds up. Now, why have I placed a j here? Just an algebraic manipulation, but what's the need for placing a j here? I would like to relate the magnetization to its maximum value, to the saturation value. What's the saturation value of the moment of when all the moments are aligned? Of course, there are n particles and the volume is V. If all the particles are aligned, they will have the same magnetic moment, and the magnetic moment of each one would be Gj mu B into the maximum value of Mj. The maximum value of Mj is J. So this thing is nothing but the saturation magnetization. So the magnetization as a function of the saturation magnetization is equal to this function. And I can even put a J in here, and I can divide by J in here. Okay, there's no problem in doing that. Okay, I can multiply and divide by J's. So this function is called the Brillouin function, Bj, as a function of y, where y is equal to j times this j times x, j times x. Okay, so the Brillouin function is defined in this fashion. So this magnetization is nothing but the Brillouin function. Okay, so this is just a definition of the Brillouin function. So now what we would like to do is we would like to plot versus y. Y is this thing here, m over ms. For a spin half system, we define y to be equal to mu b b over kbt. Here we are defining our y to be equal to x times j, but x is defined here. This is the same x, gj mu b b over kbt. Okay, so y is being defined as j times x, and x is nothing but gj mu b over kbt. For a spin half system, we already know, and of course there's a b as well. We already know that for a spin half system, what we have is j is half and gj is 2. So this thing goes away, and you reproduce the result for a spin half system. So for a spin half system, we have the tangent function. Okay, we would like to plot the Brillouin function on top of this function, so that we can compare how a spin half system does with a spin j system. So for that, let's resort to a mathematical program so that we can plot this function. Okay. So we would like to plot the magnetization of a material, arbitrary spin j that is, with respect to spin half particle. So for plotting things of this kind, I use Mathematica. The first homework actually I would also like you to do some plotting, the first homework which I am still preparing. Anyway, if I plot, okay, let's do it afresh. If I plot the tan hyperbolic of some function y, now y is proportional to field over the temperature. Higher the field, higher will be y. Lower the temperature, higher will be y. So this is for a spin, this is the magnetization for a spin half paramagnetic system. And I plot y, say from -1 to 1. Okay, and if I make this plot, this is what I get. This is a spin half system. Okay, and I can increase the limits here. I can increase the field strength, so lower the temperature. The magnetization of a spin half system looks like this. Now I would like to plot the Brillouin function, which means for an arbitrary spin system. I've already defined the Brillouin function here. Okay, so my Brillouin function, of course, it depends upon the value of J. So the Brillouin function I'm defining as the function, it depends upon J. Of course it depends upon J, and it depends upon Y. So it takes two parameters, J and Y, and this is how I've defined it, and this is exactly identical to what we wrote on the blackboard. So I've defined this Brillouin function. Now I would like to plot this with respect to Y. Y is parameterizes the field strength over the temperature. Okay, and using the same variables on the x-axis. And I choose a J equal 1. So I have a spin 1 system, a boson, like a deuterium nucleus. Okay, that's a spin 1 system. Okay, and I plot with respect. So what I would like to plot is Bj, J is 1, and I would like to plot with respect to Y. So I keep Y as a running variable, and my Y now varies from -3 to +3. This is what I get. This looks quite similar to what we get for a spin half system. If I increase the value of J, so I have a quadrupolar system, which means a spin 3/2 system, for example, this is what I get. So you see slight changes in this pattern. Okay. Now I would like to plot everything on top of one another so that we can make a comparison. So what I would like to do, I would like to plot the tanh function with respect to Y, and a spin 1 system. So I'm keeping the Y variables same, and I'm plotting both of these functions on top of one another. The blue function is the spin half system, and the purple function is the spin 1 system, the magnetization of it. I can even go further. I can plot a spin 3/2 system on the same graph. So all of these lines take the same general shape, but they are different, and experiments will tell you if you measure the magnetization as a function of temperature, you can tell what the spin of the system is if it's really a paramagnetic material. If I increase J to a really large value, say 100, this is what I get. If I increase J to an even larger value, so I have a spin 1000 system, then all the lines will start collapsing onto one single line. So the J100 and the J1000 systems are collapsing onto the same line. So these lines asymptote to a particular function, and that's the asymptotic value of the Brillouin function when J approaches infinity. Then the Brillouin function is called the Langevin function. So if I put J equals infinity, then the Brillouin function approaches to another function which is called the Langevin function. So for a spin half system, the blue curve represents the magnetization. For a spin 1 system, this curve represents the magnetization as a function of field over temperature, something proportional to the field over the temperature. And for higher and higher spin systems, this graph approaches this shape. And for each one of these graphs, you can see what the high temperature approximation is. Remember, lower values of Y represent higher temperatures. So for each one of them, you could do a series expansion about Y, truncate the higher order terms, and find out what the magnetization is as a function of temperature. Okay. For example, if I have Bj J equals 2 and Y here, and I do a series expansion of this with respect to y. Now y goes from 0 to, I would like to take 6 times. So you see, this is a series expansion of the magnetization as a function of y. Y is field over the temperature. So the lowest order term shows the Curie kind of behavior, because y is just b over t. So to lowest order, this spin J system, J is now 2, also obeys the Curie law. Its magnetization is inversely proportional to the temperature. In the high temperature approximation, remember, because y becomes successively smaller as you increase the temperature, and the higher order terms can be neglected. But if the temperature is not large, which means you are at the low temperature approximation, you have to use the full curve of the Brillouin function. Okay? So you can do series expansion to find out what's the high temperature approximation of these magnetization curves. So this is all that I had to talk about spin J, arbitrary spin systems. Now let's move on. Let's resort to the blackboard again.
सर बस लगा दें
नहीं ना वो स्विच खराब है. So far we've talked about the energy of a dipole when placed inside a magnetic field. Now we would like to talk about the forces on dipoles when they're placed inside fields. Alright, so any questions about paramagnetism? What real systems are paramagnetic? We'll have more to talk about this in the course. So rare earth systems or rare earth ions, they are paramagnetic. A solution of iron chloride will be paramagnetic. A solution of manganese chloride will be paramagnetic, etc., etc. We'll talk more about what real systems correspond to paramagnetic systems. We'll talk more about this in due course. However, let's now talk about the second aspect, which I promised. The force on a dipole when placed inside a magnetic field. So we know that the energy E is given by minus mu dotted with B, and forces in general are given by the negative of the gradient of the energy. Okay? This means that the force in general will depend upon the dot product, the gradient of the dot product of u and v. Now if we do a vector expansion of this, use a vector identity and assume that there is no gradient in the magnetic moment, which means that the magnetic moment is really small in space. Okay? And there are no time varying electric fields, which means that del cross B is 0. Then this thing is simply given by, the force is given by mu dotted with del product with the magnetic field. Okay, so this is the force on a dipole. Okay, you have to use a vector identity to expand this, and the assumptions that I made that the mu is really small. Now let's look at this particular aspect. Suppose I have a magnetic field which is pointing solely in the z direction. Okay? So the field is pointing solely in the z direction. It could be an inhomogeneous field. So the field could look something like this. At small values of z, you have a field that's pointing in the z direction, At higher values of z, you have a bigger field still pointing in the z direction. Here you have a bigger field still pointing in the z direction. Okay, so the field is always pointing in the z direction, and its magnitude is constant in a yx plane, but it's constantly increasing in z. So it's an inhomogeneous field. So suppose you have a field of this kind. So the field only has a z component. Okay, so it only has a z component, and its magnitude depends upon z. Okay, so this is your magnetic field. Inhomogeneous, not uniform. And we all know that mu could be arbitrary. Okay, so if I take the dot product of mu and del, the dot product of mu and del will give me something, and the force turns out to be the following. The force is mu x Now the field only depends upon the z variable. So this goes away, and you're left with mu z dv over dz. Since you have variation, I've replaced the partials with proper differentials, and this is easy. So the force is now pointing along the z direction. And if mu z is quantized, which we know it is, then the force is also quantized. And remember, a force will be non-zero. It will exist only when this thing is non-zero, which means whenever we have an inhomogeneous field. So if you have a magnetic moment passing through a uniform field, a homogeneous field, no force can act on this dipole. Alright? So forces act on dipoles whenever there is an inhomogeneous field. A magnet is able to attract a piece of iron or another magnet only because the field of this magnet is non-uniform. If the field of this magnet were uniform, you would never be able to discover magnetism in the first place, because there would be no forces of attraction or repulsion. So thanks to the non-uniformity of the magnetic field, that magnetism was discovered, say, 5,000 years ago. Right? So you require a non-uniform magnetic field to produce a force on a dipole. And this was the original idea behind in Stern and Gerlach's mind as well, in which they had an oven which produced silver atoms at high temperature. They were fired off from an aperture inside the oven, and then they had a non-uniform magnetic field provided by tapered pole pieces. Okay, so these tapered pole pieces, which were engineered in a special fashion, produced a non-uniform field. Now I am drawing the streamlined picture of the field, in which the density of the lines show the magnitude of the field. So the field is stronger here. So dB over dz is positive if I take this to be the z direction. So if I have spins coming in, spin half particles coming in, and they traverse this inhomogeneous species, a force will act. The force is going to be in the z direction, and the magnitude of the force depends upon this. Now this thing is engineered by the magnet, so dB over dz is increasing in the positive direction. And if they place a screen here, they observe two distinct spots here, which means that the force is of two kinds, positive and negative. Which means that mu z is quantized, it's of two kinds. Mu z is plus some mu or minus some mu. Okay, this is how the idea of quantization of spins was discovered. In fact, these silver atoms have a single electron in their valence shell, in their s orbital, in the valence s orbital. That single electron has a magnetic moment mu b, You place it inside a magnetic field, the moment could be plus mu b or minus mu b. Hence, the force that acted on these silver atoms, which carried the lone pair of electron, was plus mu b dB over dz or minus mu b dB over dz. Hence, because of these forces which take up quantized values, discrete values, this beam could be steered in the upward direction or in the downward direction. Alright, and you get two distinct spots. And these two distinct spots tell us that it's a spin half particle. Now, and you could determine what the spin mu b is, because you know the length of these magnets, you can find out what the forces are. You know what the speed of these silver atoms are because you have a velocity selector placed here. Okay, so this is how the idea of the spin came about by Stern and Gerlach and by Goudsmit, and they could actually calculate that the spin, this magnetic moment is related to the spin. The magnetic moment we all know. Any magnetic moment is given by G E over 2m ns h bar, right? So if you could find mu, you could find ms. Ms turned out to be plus half or minus half. So electrons spin half particles. Everything else is a constant here. So you measure spin's quantization indirectly by the forces on the spins, and for that you need inhomogeneous magnetic fields. So this is an idea where the force on a dipole is important. We have another idea. Now, could you perform the same experiment with electrons? Suppose you have a stream of polarized electrons. Polarized electrons means that all the electrons have a moment pointing in the same direction. Somehow you prepare them. Now, what's going to happen to these? Could you perform a Stern-Gerlach experiment with free electrons in space? So these electrons are harbored inside silver atoms. So this experiment was easy. So the silver atoms carried the valence electron. So the entire atom was moving. So this is a beam of atoms, not a beam of electrons. Even though the lone electron, that spin is uncancelled. So the spin of the atom is the spin of the electron. But nevertheless, it's a beam of atoms. It's an atomic beam. Could you perform the same experiment with free electrons? You can produce free electrons through thermonic emission. That's what the old TVs did. So can you do this experiment with electrons? Just think about this for half a minute. And suppose the electrons are all spin polarized. So if we were able to do this with electrons and all of them were pointing in one direction, you would get a beam upward. Or if all of them were pointing downward, you would get downward beam. If you had an unpolarized beam, half of the intensity of electrons would go here and half would go here. But could you perform this experiment with just electrons? Free electrons. Okay, think about the charge. What's the charge on a silver atom? Zero. The silver atom is uncharged. Okay, but what about an electron? It carries charge. So, could you now answer my question? So now if the electron carries charge and it passes through a magnetic field, what's going to happen to the electron? It's going to experience a Lorentz force. The Lorentz force is given by, for an electron, it's given by minus E V crossed with B. So if an electron was moving in this direction and the field was pointing upward, you would have a force that's pointing in this direction because it's a negatively charged particle. So you would have a force in this plane. Okay? So the force will change. So it's not easy to perform the same experiment with free electrons, but nevertheless it is possible. And this idea is actually exploited in the measurement of spin polarization of electron beams. And the idea is embodied by a special type of detector called a Mott detector. Suppose you have a single atom, like a gold atom. This is the nucleus of the gold atom. And a beam of electrons is coming in, right? It's approaching this atom here. And this beam of electrons could be spin polarized or not. Now what happens is, when these electrons are high energy electrons, they approach the nucleus is positively charged. Okay? So now the electrons have entered the atom. In the rest frame of the electron, the nucleus is moving towards the electron. Now the nucleus is positively charged. So now an electron beam is firing onto this silver atom that could be a part of a gold foil, a thin gold foil. And what the electron sees is that the nucleus is coming towards it. So it sees a positive current coming towards it. Now if you know your basic electromagnetism, you have a current pointing out. That current pointing out will produce a magnetic field. So the electron sees a magnetic field. So what's the direction of that magnetic field, by the way? If an electron impinging upon this atom. So the current is coming towards you. So it's going to be anti-clockwise. So an electron sees a counter-clockwise field. And is the field uniform here? Is this field uniform in space? You have a current carrying conductor or a current. Is the field uniform? No, it's not. It's given by Ampere's law. It falls off inversely at the distance from the nucleus. It's mu naught I over 2 pi r, if you remember. So the field is strong here and the field is weak here. You have a gradient of the magnetic field. So you have a strong field here and you have a weak field here. You have a strong field here and a weak field here. So you get a gradient in the magnetic field. Now you have a magnetic dipole, an electron whose spin is pointing in the up direction. It's coming in, and it's coming to the right of the nucleus, right? It's coming in here. Now the magnetic field gradient is in this direction. So this electron beam will be steered towards the left because there's a force. Suppose the force is in the direction of the field gradient. So an electron that's coming in under the action of this field gradient will experience a force towards the left. Here, the direction of the field gradient is in this direction. Okay? So now an electron that's pointing upward, whose spin is pointing upward, sees some field gradient. Okay, and it's in a particular direction. So electron beams will be steered towards the left or towards the right, depending upon whether they are coming into the left of the atom or to the right of the atom, and depending upon whether the spin is up or down. Okay, so if an electron's spin is pointing in the upward direction, so mu z is suppose positive. When mu z is positive, this electron experiences a force to the left. So this electron beam moves towards the left. Okay? And if the electron were pointing in the negative direction, it was polarized in the opposite direction, then when it reaches the atom to the right of the nucleus, it will be pointing in the beam of electrons will be deflected towards the opposite direction. So you can separate out the beam of electrons depending upon the spin of the electrons. So you have a beam of electrons coming in and you have spins that are either plus mu b or minus mu b, and these are free electrons. And when they approach the atom of a single atom, say of gold, depending upon their polarizations, these electrons could be deflected in opposite directions. So this is spin dependent scattering. Okay, so you get Mott scattering or spin dependent scattering because of this effect that the nucleus acts like a current, it produces a non-uniform magnetic field, and that non-uniform magnetic field is sufficient to steer the electrons depending upon the relative polarization of electrons. And if you have a detector here and you have a detector here, the intensity on this detector minus the intensity on the other detector will give you the degree of polarization of the initial beam of electrons. So another technique in which the force acted upon on dipoles is important is the technique of magnetic force microscopy. Okay, and I have, towards the end of this class, I will show you some slides that actually, from real papers, that actually show this process in action. There again, there is a non-uniform magnetic field that produces a force on a material, and that force is registered by the change in the oscillation of a cantilever, which is then detected by a suitable mechanism. Okay, so a third application is magnetic force microscopy, and in fact with this technique you can find out the spin of a single electron. You can detect the spin of single electrons. Okay, now let's talk about the third component, which is the torque acting on a dipole. Okay, any questions so far about forces or energies? So if I have a dipole mu and it is placed inside a magnetic field, what's the torque acting on the dipole? This is mu cross with B. Okay, this is something you learn from basic electromagnetism. So if I have a magnetic field that's pointing in the up direction, okay, and you have a moment that's pointing in an arbitrary direction, tau, like this. Oh, sorry, a moment. This is a moment. So your moment is pointing like this. What's the direction of the torque here? Outside. So the torque is now pointing out of the plane of the black hole. Okay. If the field direction is reversed, the torque direction is also reversed. So whenever you place moments inside uniform fields, there can be no forces, but there still can be torques. In order for forces to act on dipoles, you need to have inhomogeneous fields. You need to have some field gradient. Okay. In fact, many catalysts work. Some paramagnetic iron oxide is an important catalyst, Fe3O4. It's a paramagnetic material. In fact, ferrimagnetic, so strongly paramagnetic. It acts because it produces a field gradient, and the substrate molecule experiences that field gradient. So there's a magnetic origin to the process of catalysis as well, especially if you're using these iron oxide based catalysts. Alright, now let's talk about torque. Now what we have is a magnetic moment, mu, placed inside a magnetic field. The magnetic field is pointing in the upward direction. A torque acts on this. Now let me draw a proper figure here. We all know from basic mechanics that the torque is given by the rate of change of angular momentum. Okay? Now I'm using this L loosely. This could be spin, this could be L, this could be some J. Okay? So let's write this as J to be exact. This is some J, an angular momentum, okay? Orbital spin or a combination of it. We know this. But we also know that the magnetic moment is proportional to J. And the constant of proportionality is the gyromagnetic or the magnetogyric ratio. We learned about this in the first class. Okay, we know this. For an electron, this is E over m, and so on. So this means that the torque gives rise to a variation in the angular momentum, and it also gives rise to a variation in the magnetic moment. So this is 1 over gamma d mu by dt. So this is the torque. Now this means that 1 over gamma into d mu by dt is equal to mu cross with B. This also means that mu cross with B equals the magneto-gyric ratio into mu cross. This is D mu over dt. So the rate of change of magnetic moment is given by this. This is called, does anyone know what this is called? This is called the Bloch equation. Okay, and this can be solved for the magnetic moment, which now becomes a function of time. So let's solve this equation once on the blackboard, and then we'll resort to the computer to find numerical solutions. Suppose the magnetic field is pointing in the z direction. It's a uniform field. Okay, and suppose that our magnetic moment mu, of course it's a vector. It will have an x component that depends upon time, a y component that depends upon time, and a z component that depends upon time. So in short, we would like to solve this Bloch equation to find out the time evolution of the magnetic moment when it is placed inside a magnetic field. There is a torque. So how does the magnetic moment turn with time? For example, inside a motor, which is everywhere these days, you have a magnetic field and you have a current carrying coil which has this magnetic moment. A torque acts on that coil and the coil starts rotating. It's the same thing, even though our coils are now atomic species. Okay, so these are atomic motors, in other words. We would like to see how the magnetic moment evolves with time. Now the field is pointing in the z direction. So let's find mu cross B. Let's do a simple calculation for mu cross with B. Mu cross with B, let's find this out, is I, J, K, unit vectors, mu x, mu y, mu z, 0, 0, because the field only has a z component. Okay, so this is I, mu y b, mu y b, okay, minus j, mu x b, okay, and no k component. So the torque really is, or d mu by dt is given by this, which means that d mu x by dt is given by mu y b into gamma, d mu y by dt is given by minus gamma mu x b, and d mu z by dt is given by 0. So which one of these equations is the easiest to solve? The third one. This should actually mean that mu z, whatever it is at time t equals 0, it remains the same. It remains constant. Okay? So nothing happens to mu z. Which means that if the magnetic moment was making a certain angle on the z-axis, it will remain at that, making the same angle of co-latitude with the z-axis. It's not going to change. However, mu x and mu y can change. Now, if I look at the first, I can solve this. This is just a simple exercise. You can solve this equation. For example, you can take the double derivative d square mu x over dt. Square is gamma b dy over dt, but dy over dt is minus gamma square mu x b square, right? Okay, let's do this properly. So this is gamma b d mu y over dt is minus gamma square b square mu x, right? Okay, so now I can solve this equation. This equation can be solved quite simply. D square mu x over dt square plus gamma square b square mu x is 0. Now what's the solution of this equation? How do I solve this equation? What's the solution? It's an oscillatory solution. So mu x turns out to be, as a function of time, this turns out to be some constant cosine of omega t, and omega is gamma b t. Some constant here, let's call this small c naught plus c1 sine omega bt. Correct? And I can use initial conditions such that c1 equals 0. So initially my x-axis, my moment is such that the moment is pointing along the x direction. So I can put this thing to be 0. I can have some constant c cosine of gamma bt. Then my mu y is going to be equal to c sine of gamma bt. And my mu z as a function of time is that it's not a function of time, it's just some constant. So now what I have is, I have a magnetic field that's pointing in the upward direction. I start off with a magnetic moment that's pointing in this direction. My axes are such that this is my x-axis, my y-axis and my z-axis. Now this system is going to evolve with time in such a manner that it's going to precess around this z-axis, which is the field axis. Remember, you apply a field, it breaks the symmetry. That axis becomes your quantization axis. So now this magnetic moment is precessing around the z-axis such that its z component, which is simply the projection on the z-axis, remains constant. So it moves on the mouth of a piece of a cone. And what's the frequency of oscillation? What's the frequency here? Omega. It's gamma b. Could be minus gamma b, but that's immaterial. Okay? So it's gamma b. It depends upon the gyromagnetic ratio and the magnetic field. Stronger the field, stronger will be the rotation. This frequency is also called the Larmor frequency. So the magnetic moment is now oscillating in, is now precessing. This action is called precession about the z-axis, about the direction of the field. Okay? So this is a solution of the Bloch equation. Whenever you have a spin placed inside a magnetic field, a uniform magnetic field, it is going to precess with a certain frequency that is characteristic of that spin species. Remember, gyromagnetic ratio depends upon lambda g factor and the magnetic moment and the spin. So if you can measure this frequency, you can measure gamma, you can identify the species. And this is the underlying principle of nuclear magnetic resonance as well. NMR works on this principle. I'm not going to describe NMR here because it's going to take a lot of time, but this is the underlying mechanism of NMR, nuclear magnetic resonance. So whenever you do an MRI scan, God forbid you have some ailment and you are asked to do an MRI scan, it's basically quantum mechanics at work. The spins are at work over there. Okay? The Bloch equation is really at work. Now this equation that I've written over there, this equation is called the Bloch equation. Okay, and under certain conditions with the uniform field, these are the Bloch equations. But what happens in real systems, in a solid or any real system, is that this system is actually going to relax with time as well. Now look what's going to happen. If you look at the direction of the torque in this case, the torque is pointing outward. Okay? So if I draw that outward by this vector tau, okay, this is the torque. It's pointing outwards. Now this shows the change in the magnetic moment with respect to time, because tau, as you all know, gives you the rate of change of d mu over dt. So these two things are parallel if gamma is positive, and if gamma is negative, these two things are anti-parallel. Okay. For an electron, for example, gamma is negative because the charge is negative. So for an electron, this is the direction of d mu. Okay. Now what really happens is that the system, in a real system, actually comes back in such a manner that it comes back parallel to the z-axis, because that lowers the energy of the system. So what's going to happen is that a damping torque acts. Okay, so this is a coherent torque. This gives you coherent oscillations. It is describable with coherent quantum mechanics. It's an SU2 operator. So it's a unitary operator, this precession. However, due to damping, some relaxation mechanism as it is called, there's a torque that acts so as to bring this magnetic moment parallel to the z-axis. Okay? Because that's the lowest energy state. You see, you have an energy consideration and you have an angular momentum consideration. The angular momentum consideration makes this spin go or precess around the field. But then the energy consideration would like the system to relax to its ground state. So what happens is that torque acts in this direction. This is, let's call this the damping torque. Okay. Now this damping torque will make this magnetic moment with time, with a certain time constant, the relaxation time constant, go back so that it comes parallel to the direction of the z-axis. So now we can phenomenologically or empirically come up with what this tau sub d is. Phenomenologically, this tau sub d can also be written as a cross product. If I write this, okay, can I take any two vectors inside this diagram and form a cross product between those vectors, and the cross product is along tau d? Can I identify two such vectors? You see, torque is mu crossed with a magnetic field. Okay? So I would like to write this as a cross product of two vectors. What two vectors could I take here by looking at the diagram? So one of them could be, this is mu, right? Could be mu. If I take the cross product of mu with this, I will get this vector. I will get a vector that's along tau d. Okay? So this mu is upward, this is making an angle, and I take the cross product with d mu, I will get something that's perpendicular to the plane, right? Remember, this is in a plane, this is also in a plane. This plane is pointing inwards, this d mu is pointing inwards, okay? So I have a plane like this. My mu is like this. This is my mu, and this is my d mu. Okay? In other words, my mu is like this. So if I take mu cross d mu, I get something that's pointing upward towards the z-axis. So this tau d could empirically be written as a cross product of mu with d mu by dt, right? This is an empirical relationship. Okay, and this gives a dissipative torque in the proper direction so that the system relaxes back to its ground state. And this is an extremely important process, this relaxing back. It's called relaxation, or it's also called decoherence. Every spin is going to decohere with time. Boltzmann distribution ये कहता है कि this is the lower energy state. You have to have a Boltzmann distribution of spins, and in order to achieve that Boltzmann distribution, the system must equilibrate, must come to equilibrium. So the desire of systems to come to equilibrium is causing this dissipated torque. Now there could be different physical mechanisms. There could be phonons, there could be lattice vibrations, there could be some other degree of freedom which is taking up the energy, which is generally called a lattice, which is physically causing this dissipation. Okay. So now this tau d is proportional to this, and if I want, I can put some parameter alpha with this, just to give a proportionality, right? Some alpha. It's a dimensionless number, but it can only be dimensionless if you divide this by the magnitude of the moment mu, because you have a mu here and then you have a d mu here. So the numerator is proportional to mu squared. So you would like to put a mu here as well. Okay. In other words, this d mu over dt divided by mu has the same dimensions as the magnetic field. Okay, so for dimensionality, consistency, you have to put this mu in here. So now what the block equation tells you, the block equation is slightly modified. You have a real torque, a coherent torque, which is causing the precession of this magnetic moment in the field, and on top of this you have this dissipated torque. Okay. So now the equation is slightly modified. The equation is modified in this fashion. The torque, okay, d mu over dt, d mu over dt torque, can mu cross with B. Now d mu over dt is equal to gamma mu cross with B. Okay, this is the coherent term from the block equation, plus alpha over mu, the dissipative torque. Now the dissipative torque is given over there, mu crossed with d mu by dt. Okay, am I putting the other dimensions all right here? d mu by dt. एक मिनट. Oh, there must be a gamma here too, right? Okay, there must be a gamma here as well. So this equation is called the Landau-Lifshitz equation. Now you need to solve this equation. Okay, you need, now the problem here is that you have d mu over dt here and you have d mu over dt here. Okay. So what you would like to do is you would like to pick up this value of d mu over dt and put it in here. So you would like to do a recursion. So what you would like to do, you would replace this d mu over dt, okay, by all of this. And when you make this replacement, you get mu cross with mu cross b, and you get mu cross with mu cross d mu by dt, and then you use certain vector identities to have an equation in which the right hand side is devoid of d mu by dt. It's an algebraic step that you need to perform, and the final result that you get is the following: d mu by dt 1 plus alpha squared, which is just a phenomenological constant, is equal to gamma mu crossed with b plus alpha gamma over mu into mu crossed with mu crossed with b. It's a nice analytical form that we obtain. So this is the Landau-Lifshitz equation, which is a phenomenological equation. This is coherent. This is a phenomenological term that is added to describe the decoherence or the relaxation. And then in order to get rid of this term which appears on the right hand side, you would take the value of d mu by dt, which is all of it, and put it in here. And then you use the vector identities to simplify. You will get this expression. This is a famous equation which is called the Landau-Lifshitz Gilbert equation, or the LLG equation, or the LLG damping equation. You can solve this numerically if you have a magnetic field that's pointing along the b direction, and you know the gyromagnetic ratio, and you can solve this equation for mu as we solved the Bloch equation. And this is one homework problem, by the way. Alright? So decoherence takes place. This equation, the Landau-Lifshitz Gilbert equation, tells you what happens to spins when they are placed inside a magnetic field and how they relax with time. The second equation is the Bloch equation. The Bloch equation is a nice coherent equation. And on top of it, we've added a damping term to get the Landau-Lifshitz Gilbert equation. Now the Bloch equation can also be adjusted. This equation can also be adjusted to account for relaxation. And the way you would do that is in the following fashion. d mu x over dt, which is simply given coherently by gamma mu y over b. If you solve this equation, you get the precession. However, if you phenomenologically add another term to it, which is minus mu x over t2, okay, but this t has dimensions of time, okay. Can you imagine what is going to be the effect of this additional term on this equation? If I were to plot versus time mu x for the normal Bloch equation, that is just this term, of course I get an oscillation. The oscillation frequency is gamma b, the Larmor frequency. Now what's going to be the effect of the addition of this term on this magnetic moment? Damping, मैंने आपके होंठ पढ़े हैं, damping, alright? An exponential damping. Suppose I don't have this. You solve this equation, you get a damping term. Or, right? So the effect of this is that this function, which was oscillatory up to time infinity, is now going to damp with time. Okay? And the damping time constant is given by T2. This T2 is called a spin damping time constant, or it's also called T2 relaxation. It's like spin diffusion relaxation. There are different names for it. This gives us a coherence time for the spin, right? If our time of observation is smaller than T2, we will assume coherent oscillation. Otherwise, if our time of observation is larger than T2, because this is the characteristic time scale over which the magnetization or the spin is going to decohere. Okay? Likewise, d mu by dt, I can have a y here. If I had a y here, I had an x here and a plus here, and a y here. So x and y components, both of them damp with the same damping time constant T2. Likewise, if I have d mu z over dt, this is constant, this is 0, and I can on top of this add a relaxation which makes this magnetization go back to the z-axis. You see, what is mu x and mu y? What is this T2 constant doing? It is decohering mu x and mu y. So something's dephasing. But what this kind of relaxation is going to do is, let me first explain this. Mu z is the z component of the magnetic moment, and mu naught is the equilibrium magnetization, is the equilibrium component, z component of the magnetic moment. In equilibrium, it's mu naught. So, how far is your instantaneous magnetic moment z component from its equilibrium value divided by a time constant? This will tell me how fast is my magnetic moment approaching its equilibrium state. T2, the T2s are giving me, if I have mu x, how fast is that mu x decohering with time. And T1 is giving me the spin lattice relaxation, which is telling me how fast is my magnetic moment achieving its resorting back, equilibrating, coming back to its equilibrium position. Now I have, in the last 2-3 minutes, I would just like to show a simulation which will actually bring home these ideas. So I've written a MATLAB code. Okay, let me, first of all, what I've done in this code is, let's see, I have defined an initial magnetization with theta is 90 degrees. So I'm starting off in the equatorial plane. So my magnetization moment is lying in the xy plane, phi is 0, and I have time constants, large time constants in seconds, 100 seconds, and t1 is 100, right? So these are large time constants. By the way, I'm using dimensionless units here. And I plot the trajectory from 0 to 100 seconds, assuming my Larmor frequency is 1, which depends upon the gyromagnetic ratio kind of spin. So this is my initial magnetic moment, right? In order to solve an equation, I need an initial condition. This is my initial condition. This is my solver. The block equation is defined here in different function file. This is simply the block equation with the t1 and the t2 terms added. Okay, so I've defined a function for this. Then I have a solver, MATLAB's famous OD45 solver, and I plot the trajectory of the magnetization with respect to time. This is one thing that I do. In the next part, I make another figure in which I draw a sphere just for easy visualization, and then I plot the magnetization trajectory on that sphere. Okay, so now I'm going to run this code. So it's solving the equation. Okay, I'll run this again, but for the time being, okay, let's first look at this equation, at this solution. So here you see three curves. I'm plotting the x component of the moment, the y component of the moment, and the z component of the moment. Initially, my z component was 0 because my moment was lying in the xy plane. With time, this is approaching an equilibrium value 1, right? You see the z component approaching an equilibrium value of 1. This means that this magnetic moment, which started off here, is slowly approaching the z-axis, becoming parallel to the magnetic field because it would like to equilibrate. And the time constant for this is t1 in the Bloch sphere model, in the Bloch equation model. And if you look at the red and the blue curve, these represent the x and the y components of the magnetic moment. Both of them start off at some value. X component starts off, say, at probably 0, y component starts off at its maximum value. And then they oscillate. The frequency of this oscillation is given by omega, which is 1. Okay? The time period is going to be 1 unit here, right? These are units of time. And both of these components are damping with time, and the time constant for this relaxation is t2, is 100 seconds. So in about 100 seconds, this thing is going to drop to about 37% of its maximum of the value from where it started. So now I've phenomenologically modified the Bloch equation by plugging in by hand relaxation time constants. And this is how a spin will actually decohere with time. It will relax with time. And in the second part of this graph, what I've drawn, now I will rerun this program so that you can look at this trajectory as it evolves with time. The red arrow is going to show you the magnetization or the magnetic moment. I can talk about the moment of a single spin or the magnetization of the entire volume, right? Both of them will be proportional in the macro spin model. So the red arrow is going to show you the trajectory of the spin with time, and the black, these black are just going to retrace the trajectory. Okay. So I'm going to rerun this program, and you can focus your attention on how the system is going to relax with time. Okay. You see the x and the y components, both of them are decreasing in magnitude, which means they are dephasing, and the moment is also tilting towards the z-axis. This is what the trajectory is going to look like, and I can vary the orientation, the viewing of this, right? This is what it's actually looking like. See, it started off in the equatorial plane, then it waned, it slightly damped. So it's damping in the xy direction with the time constant t2, and it's also shifting towards the z-axis. If in the last, if I would just like to change this to really small numbers, okay, if I change t1 to a small number while keeping t2 constant, you see, I can see the variation of it, right? Now, what's going to happen is that the approach to equilibrium is really fast, and the damping along the xy direction is really slow. I've adjusted the t1 and the t2 values. So different kinds of behaviors are observed. In a real solid system, these spins are going to relax with time. And the modified Bloch equation or the Landau-Lifshitz-Gilbert equation is going to model this effect. So I've made this program for the Bloch equation, and as a homework I'm going to ask you to just copy my program and modify it and implement the Landau-Lifshitz-Gilbert model. Alright? So see you next week. Thank you very much.